Hi everyone. I'd just like to thank Alex for letting us speak today to you about a little bit about what we're trying to do here at Plastech in regards to introducing some new building materials to the market. Doesn't seem to, there we go, always technical difficulties with Teams. So just a little bit about the two big picture global problems that we're trying to solve. The first is sand usage, which I'm sure probably some of you are aware of. The rate at which we're using sand that is suitable for construction is just far too much, and it's actually more than nature can possibly produce. So the world is actually, in fact, running out of sand, usable sand for construction anyway. So alternative materials are having to be sought after. And a much more well-aware problem globally, and especially in the UK, we kind of see it everywhere now, is the problem of plastic and the fact that a lot of this plastic, in fact, 91% of it is still not actually recycled. And this is for numerous reasons. It can be that the plastic itself actually isn't recyclable, mechanically that is anyway, or that it's not desirable. The waste management companies have other streams of plastic that is worth a lot more money, so tend to focus on them. So what we as Plastech try to do as a company is we take these sources of plastic that are either unrecyclable or undesirable to waste management companies, and we transform them into a material that can replace sand in concrete. And why you would want to do this, other than obviously just trying to look at uses for plastic, is in fact that it actually improves the properties of the concrete. So it lightweights the concrete, it can severely reduce the carbon footprint of the concrete, and also add thermal insulation. And the the process that we actually do for this, we have patent pending status on. So a little bit about the company and sort of what we are and where we came from. We're very much a startup company. We're a small team of 3 at the minute who all graduated Durham with PhDs in chemistry. We incorporated back in 2019, but we've really sort of only geared up and really full-time been working on the business since August this year. And that was because we actually came into some funding through Innovate UK and some venture capitalist funding that is actually funding the R&D research that we're doing at the minute. And the process that we have developed to do this is we look at the input raw material. Like I said earlier, we try and focus on plastic that can't be recycled or that is difficult to recycle. And then we mechanically process it through steps that are very widely used in the recycling industry already, including a granulation step, which is where basically they are just blades that spin round that can size reduce material. And the reason why we do this is because a lot of the material that we get actually has to be pelletized. So usually plastic waste is either landfilled or it's sent for incineration. If it's sent for incineration, it actually has to be pelletized, almost like, so it looks like animal feed, into pellets so it can be burnt. So we need to break those pellets back up, which we do in this step. And then we use simple mechanical methods to size separate and reformulate the plastic into a distribution that is suitable to be used in concrete. We then have our sort of special source step, so to speak, which the patent is on. So I can't really go into too much detail about that, unfortunately. But here, this is where we actually change the plastic so it can actually be used in concrete. Because if you were to throw just normal plastic into concrete, the resulting material properties aren't that great. And so we change the plastic so it can actually be incorporated into concrete and keep the material properties good. And then obviously we do a lot of testing at the minute. So this is very much the staging that we're in. We're making a lot of cubes. I mean, a lot of cubes, and just testing the material properties with different formulations to try and optimize the mix designs going forward. So the products we have in development at the minute, the primary one that we're working on is an ultra lightweight thermally insulating aggregate that we're looking to be used in blockwork and concrete masonry. So these could be replacements for your sort of aircrete blocks or your lightweight aggregate blocks that are used in a lot of house building. And we can already, there's a lot of optimization that needs to be done, but already we're seeing that we're getting material properties out of this that are very, very similar to what's on the market. So we can get low densities, so they're easy to work with. We can get compressional strengths that hit the specifications needed for block work for housing. And we're getting really low thermal conductivities, which is great because it means these blocks can be used as a insulating material. And as well, when we're looking at housing, that is a really desirable property because going forward it can reduce bills, etc., and energy usage in that way. So that's the primary project that we're working on and we're taking forward. Another thing that we are also looking at, and this is sort of an outcome that we didn't necessarily expect, but we found from when we started to use our material in the blockwork applications, was that we found that it actually increased the curing rate of the concrete. And so we've started to look at optimizing this a bit further to look at creating an accelerated curing admixture, which would be more of an additive rather than an integral raw material of the concrete. And so far, like I said, very preliminary results, but we found that adding this additive, which again is made up of complete waste plastic, increases the strength of the concrete by roughly 26% after just one day. And so we're hoping to optimize this and get that percentage higher. But back onto the block work, which is what we're really focusing on. The actual material that we use is old insulation. So a lot of insulation is plastic based, and it's a type of plastic called a thermoset plastic, which means it actually can't be remelted down. And because it can't be remelted down, it can't be used in a lot of the recycling processes that are present currently. And so therefore it is sent abroad to be incinerated. And when this material is incinerated, all that carbon that is trapped in the plastic is released into the atmosphere. So it's really not great. And so just to sort of have a look at the lifespan of materials that we're looking at, we sort of, apologies, we look at plastic. Once the consumer gets rid of it and it goes to the recycler takes out valuable material. So these are your things like your plastic pop bottles, your milk bottles, those sort of things that you put in your bin. The recycler will take out and they will sell them on to be recycled. And that material has inherent value and is actually really quite valuable. You're looking at hundreds of pounds a tonne. But then they also have then this waste material that either they can't get the hundreds of pounds a tonne for, or it just can't physically be recycled. Like I said, this is pelletized and then it's transported, usually abroad, just because a lot of the incineration plants in the UK are actually at capacity. So this is usually have to be sent overseas, which is then incinerated. So if we can use this material that is sent abroad and incinerated, then this CO2 that is released into the atmosphere actually no longer is. And it's called what is an avoided impact. So because that carbon isn't being released, if you use it in another material, it has an inherent negative carbon number output associated with it. So if we can reuse this material, then we can start to look at making other construction materials that are either carbon negative or carbon neutral. So looking a little bit further into this carbon analysis side of things, we actually had a third-party life cycle analysis company conduct a study for us, in which it looked at the CO2 equivalent values, so emissions of our process and the resulting products compared to normal concrete and normal raw materials that are used. So they looked at different things such as different cement types. They looked at different things such as how much sand you can replace in concrete, and also the different types of plastic. And these types of plastics down here are things that you would tend to see in waste streams along the recycling journey. So just to explain this graph a little bit, all the negative gradient lines that you can see here are different types of plastic. Along the x-axis, we have the percent replacement of the concrete with sand. So because of the size distributions we look at, it makes more sense to look at sand replacements rather than large aggregate replacements. Apologies. And so along here is just, so for example, 50% would mean 50% of the sand of the mix is taken out and 50% of our plastic aggregate is put in. Along the y-axis, we just have the CO2 equivalent outputs in kilograms. And because the aggregate that we make can be used for lightweighting, we also wanted to compare this to lightweight aggregate blocks that contain lightweight aggregates. So here we have a commercially leading lightweight aggregate called Perlite to compare our aggregates against. So as you can see, at 0% replacement, so this is your sort of bog standard concrete, you're looking at a carbon footprint of around 200 kilograms of CO2 per tonne of concrete that is made. As you start to replace the sand with plastic, this drastically decreases. And where it hits the x-axis is the point where you actually have a carbon neutral block. And within concrete, the biggest carbon hitter is the cement content. There are some values associated with transportation and natural aggregates used, etc. But these almost become negligible compared to the outputs of the cement production. And so really, when we're looking here, you're comparing the amount of cement in a mix compared to the amount of plastic in a mix. And these avoided impacts, so the fact that we're reusing this plastic and it is not being incinerated and therefore that carbon is not being released, you can offset the carbon that is released from the cement production to produce carbon neutral and carbon negative concrete. One interesting thing to note actually is the blockworks that actually use these lightweight aggregates to improve material properties actually have a worse CO2 footprint output than normal concrete, and that's because these lightweight aggregates tend to be expanded clays, expanded fly ash, which needs really high temperatures and processing to actually create that expansion. So the more you use of this aggregate, you're actually increasing your carbon footprint. So our lightweight aggregate, in comparison, you can rapidly decrease that carbon footprint. So this is a bar chart just essentially showing the same thing but in a different format. So for each of the different plastics we looked at, polypropylene, polyvinyl chloride, polystyrene, polyethylene, polyurethane, and a mixed plastic stream, how much percentage of that material you would need to put into your concrete block to reach carbon neutrality. And you'll find it differs for the different plastics because of the different structures and the amount of carbon that each plastic actually contains. So if we compare a ultra lightweight thermally insulating block that we have developed compared to a standard aggregate concrete block, you can see that you have a huge carbon saving. So not only are you saving around 100 kilograms just because the block itself is a carbon negative block, but also because that is replacing what would a standard concrete block be, you also save the carbon output associated with that. So overall, you get a huge carbon saving of just over 300 kilograms per tonne of concrete. And to put that into some sort of context, that's equivalent of planting 50 trees, driving 7.5 miles, or charging 390,000 smartphones, which is quite a hell a lot of smartphones. So that's all great. We know that we can create a material that is hugely carbon negative, but it actually has to be a usable material. And so we started to look at the material properties compared to what the market leading blockwork products are on the market at the minute. So here we have our traditional concrete. We have an aircrete block, a high strength aircrete block, and a block using our aggregate. So you can see our strength here sort of sits between the high strength and the normal strength block, but that's great for us. We know that we can hit the minimum strength requirements needed for a block, and this is the biggest structural requirement when looking at the standards, that we can hit this. But what is interesting is we get thermal conductivities that are completely comparable. And bearing in mind, these blocks are considered to be like super thermally insulating. They were created to be as thermally insulating as possible, and we're already hitting values that are comparable to it. And we're also getting densities that are comparable. We're slightly over yet, but like I said, with the optimization that we're doing currently, we think we can also improve on these values. But what is great is obviously the carbon story. We could hit the material properties of a block that is on the market, but we are hugely carbon negative. We don't really know the values of what the actual full block of an aircrete block is, but we know that it must be positive because it's essentially just air, cement and sand. So it will have a considerable positive carbon footprint. So that's a little bit about sort of where we are and what we're working on. But the next steps going forward for us are to continue the in-house testing that we're conducting. We've really started to go into our product development program at the minute, and we're hoping that we'll have a lot of the data in the new year. But that is making sure that we can get the strengths, thermal conductivities, and the densities that are required for block work. And we also want to start looking at some small scale demonstration projects and prototyping with this type of material. And then moving on to next year, we're looking at scaling up the manufacture of this aggregate so we can start to perhaps initiate some sales, which will be validation of not only the product, but also the business model that we're trying to create. But we know for bringing new materials into the construction industry, it is absolutely vital that we get the certification and the external testing for people to have confidence in the product. And that will also include fire testing, which we need to perform. We're not too worried about the fire rating, even though it's plastic. The material we're looking at is inherently used in housing all over, because it's the insulating foam, and that is fire retarded to be used in that application. So we don't think we will have any problems with the fire rating, but we know it's something that we need to look at. And then moving forward further into the future, we would then look to hope to scale up, really rapidly scale up the production of this. So we can do some large scale demonstration projects and really start bringing this material into the industry. Alongside this, we know we're quite a small company, so it's vital that we sort of get partners on board, and that's something that we've been working really hard at. We have a very large concrete company actually that we're looking to potentially collaborate with, which would be absolutely great, because again, it lowers those boundaries to market to getting this material actually in the industry and being used. If we can get a large company using it and also doing a lot of validation for us. So that's all I really wanted to say about what we're doing and our sort of carbon story and carbon negative materials we're producing. But we always like to just leave on this note because it really puts into context the size of the two industries that we're looking at. And it's if 2% of sand that is used for construction was replaced with waste plastic aggregates that we're trying to develop, then plastic waste would be eliminated entirely and it just wouldn't exist. And it just shows that being able to use materials from other industries that are problematic, if we can utilize them in concrete and in the construction industry, we can make really, really impressive, huge, sustainable improvements just because of the size of the industry that it is. So these are our details about the company. I'm happy to take some questions, obviously now, but if you have any questions after the webinar, or if you just want to get in touch with us, you're more than welcome to. And those are our details there that you can find us on. But that was everything I had to say. So I'm happy to take questions, and I'm not sure if you want me to stop